Okay, let me invite all the speakers from today. Go ahead and reveal yourselves. There you go. All right. So so let me jump around, and we have a lot of fun stuff. Again, like yesterday, let me just to get things a little loose and get into some little mini debates, which are always fun.
Let's agree to disagree.
Agree to disagree, yes. Disagreement is good, healthy. So pretend you've had a few glasses of wine, and we'll go from there. So let me start, Francesca. Let me start with a maybe easy one. Francesca, what you showed us is a metacognition scheme or layer that can allow us to have the best of both worlds, it seems. So if we have something that's sort of ML-ish and something that's sort of symbolic, is there any reason why we wouldn't always want to do that? Is this actually pretty non-controversial? Like, do you ever lose by doing that? Maybe we don't ever have to make a choice.
Yeah, but I think that, putting together and being able to leverage, existing neuro and symbolic, and maybe deciding which one to, making it less ad hoc to decide, which one to use when, and to reflect on what they have done in the past and so on. I think it's a useful method, but of course it works at the level of how you combine things that you are these pieces. But in the pieces themselves, of course, I see the value of all these other techniques that we heard about this morning, and by Joshua as well, and many others, on how these pieces can build partially, or can help each other build these models of the world. So I don't see it as the solution. I see it as a possible part of the solution.
May I kind of comment on this
Yeah, of
direction?
course.
Because I've been thinking a lot about the fact that there's separation between the symbolic part and the neural part may not be reflection of how things are going on in our brain. And what, the conclusion to which I come, which is only my opinion, is that if we try to our brain, there's only one, it's all neural in our brain, right? So what is that neural net doing that's symbolic and reasoning and all that, right? And so I think there are several answers here. So one of the things that's hard with symbolic reasoning is search, and also discovery, which is like learning. And so these are two things where neural nets could be good at. So think about what we do with like RL, learning a policy. It's replacing an explicit search in the space of sequence of states by an amortized computation where you train something to kind of guess what the right sequence of actions should be. The sequence of action in reasoning is a sequence of pieces of knowledge you want to piece together in order to come up with an explanation, a plan, or whatever. So this is something neural nets are very good at, which means that the two things are not like two separate systems that communicate with each other. It's more like two different views. Like the neural net is the helper that allows the intractable part of symbolic computation to take place, whether it is to learn even what are the symbols and their semantics, but more importantly here, how to reason, like come up with sequences of symbols that are meaningfully answering the question or something like that. What do you think about this, Francesca?
No, I understand that. I understand that the kind of the system one approach in some sense is supporting
Exactly.
the symbolic one, and the
Yes.
symbolic one is not necessarily a separate one, but is built by the system one
Exactly.
methods. Um, 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 Yes, but I still struggle a bit to reconcile all the pieces of incomplete knowledge that I have in my mind. For example, I mean, the fact that at some point, yes, we gather data from the world with our sensors, with our experiences, and this is our system one way of building a model of the world that then supports our symbolic procedures. But at some point, we have in our mind these symbolic procedures that are maybe built and supported and through system one. So those symbolic procedure, we use them and they are there. After a while, they get built. And we
Yes, but
use
where are they sitting in our brain? So
No,
I
I
think
mean,
they're
I'm not saying that. In fact, in my talk, I say I'm not trying to simulate the brain. I'm trying to
yeah.
simulate and I'm trying to be inspired by the mind, not the brain, not the hardware that we use.
But
So
even if you think at that level, like where are the symbols in our mind? And I think there are some clear answers there. So the memory. So you know that a lot of neuroscientists believe that working memory is essentially discrete. So the symbols come up there in your working memory, and then working memory gets shifted into your longer term memory. So all of the symbolic statements that we have thought about are there in our memory, more or less accessible if they're older and might be harder. And so they're sitting there, and we constantly generate new ones, but it's not like we have a separate like program somewhere or data structure. It's just we keep generating new pieces of program, and we remember all the pieces, potentially remember all the pieces that have crossed our mind for our lifetime. That's where the symbols actually sit in our brain.
So let's dig in on that. This is great. You are all anticipating my questions. So as AI people, we're building things, and then we have to commit to some representation or representations. And what you could be saying, Joshua, is that you want to pursue a distributed representation. Of course, a prevailing view is that the brain neural chemical representation of at the end of the day is distributed. Now, there's some debate apparently about that whether all of it is like that. But assuming that's true, and we accept that as a constraint that maybe could also have some empirical advantages other than being a brain mimicking. But then this other thing that's sort of these discrete pieces.
It's not another thing.
Mm.
Okay, so I put out a paper recently that tries to explain from a neuroscience perspective subjective experience, which is get another discussion. But let's forget about the like fancy stuff. But the idea here is that when you become conscious of something, what's happening is the dynamics of your brain, and this is observed like biologically, is contractive. So different trajectories go more or less to the same place. So the brain is a big continuous valued, huge dimensional system, and it converges to somewhere. Now, the place where it converges is an attractor of that dynamical system. And attractors have a very interesting property that there's a innumerable set of attractors. Like attractors are mutually exclusive. So automatically, this introduces a notion of discretization because you either fall in one attractor or you fall in another attractor. So what this means is your brain converges to one of an exponentially large number of discrete objects, which corresponds more or less to a thought. And it lasts about 100 milliseconds to that trajectory. Then you can keep it for some time, but then you move on to the next one. So in other words, this is very similar to the way in like deep neural net doing language modeling, you got symbols associated with vectors. So the symbols are the discrete attractors because you either like think that thought, you see the negative one way or you see it the other way, and there's an exponential number of possible thoughts you could have, but one of them gets selected because the dynamics converges there. And that attractor has both a discrete nature because you compete against all the other attractors, and a continuous nature because the configuration of the brain at that attractor is a high dimensional vector. So it's just like, word embeddings, except it's not words, it's sentences. You got like both this discrete enumeration of all the possible discrete entities, and for each of them, there is a very high dimensional vector, which is the state of the brain at when you converge to that thought. So you got jointly symbols, is actually compositions of symbols, which is a bit more tricky, but symbols, and a real valued high dimensional distributed representation. They come together. They're not like two separate things.
Okay. And Michael, in your representation, the vector symbolic or hyperdimensional computing representation, you also have a vector for concepts. Any comment on?
Yes, exactly. Yeah. So it actually quite nicely goes by also like this sparse distributed memory, which was initiated by one of the founders of our field, Pentti Kanerva. And yeah, actually it brings also quite some benefits in representing symbols as high-dimensional vectors, and maybe like in combination with some sparsities, it can give you quite some also energy efficiency, what we also see in humans' brains. So I think, yeah. And also like this compositionality is all nicely provided by our well-defined vector operations in the distributed high-dimensional space. So I would not say that we kind of lose representational power by representing symbols in high-dimensional space.
Does anyone want to jump in?
I just want to add that there's a reason why these vectors associated to symbols have been so successful in deep learning. I mean, that's the paper I wrote in 2000 about language models using neural net. Is that they give you a huge power of generalization, because like pure symbols that don't have a symbolic embedding are arbitrarily close or far from all the others. But of course, cat and dog have lots of things in common, and their brain representations are close to each other. And so you get powerful generalization when you associate symbols with vectors, and you operate on the symbols through their vectors.
That's a very good thing to point out, I think. By the way, I'm really glad to see you're here with us, Chris.
Yes, me too. It's been a long week of travel. This was not an ideal week to travel to the UK, but I have finally made it.
No, thank
I'm
you.
sorry
Thank
to
you
have
for
missed
sure.
so much.
No worries.
Yeah, I would chime in now that I have the chance, just to complement things people have said so far, that you can train neural networks to be indistinguishable from symbolic algorithms, not just in terms of their input-output behavior, but also in the sense that they have internal representations that play the same roles as the variables in your high-level causal model. And that should be enough to kind of conceptually erode the distinction between symbolic solutions and neural solutions. And then once you see that that can happen, as Yoshio said, like you get all these benefits of having distributed representations in the sense that they're a very rich semantic space that would be very hard to duplicate if you were just writing symbols down or operating purely with a kind of algebraic solution.
So is it then that we have this other representation, which we actually do maintain and is in many of the systems we heard about, that's symbolic, just to communicate between humans or between the machine and the human, so that we can debug, we can understand it? Is that the purpose of it? And therefore we should have these two things kind of always going together. Now then we have to worry about alignment between the two. We saw in Michael's talk, for example, there's a lot of work involved in that decoding step, also in what you showed us, Chris. So this alignment problem, but is that sort of how we should think of it, that there needs to be two at the same time? Because, for example, you could say, well, one of the elegances of neural nets themselves is that there's actually only one building block. So, and with the basic neuron, you just repeat them many times, but with different settings of numbers, and you kind of get one elegant model. And similarly with logic really has one essential building block. So now as an overall system, we're talking about two essential building blocks that have to be maintained.
I want to chime in if
Yeah,
possible. Yeah, so Yosha, your this thing about discretization, how discretization happens in the brain, I think that's really fascinating. But once the discretization happens, though, there seems to be at a sort of a high enough abstraction level, sort of discrete, logical operations and reasoning seem to be happening. And I'm not a neuroscientist, so I don't know, but we are aware of the right brain versus left brain kind of difference in the nature of cognitive functions that we perform. So I'm wondering, it's nice if the overall unified neural network can explain both aspects, but I wonder if there might be a good reason or benefit in having some abstract symbolic reasoning mechanism also playing a role, at least in AI, but possibly in understanding of the human cognition too.
Yeah, absolutely. I think I talked about abstraction and compression earlier in the discussion. So there's neuroscience evidence from Stan DeHaan's group, for example, that humans compared to other primates, I think more work needs to be done to extend these results, but it looks like our working memory, so the place where the symbols emerge in our mind, is doing a compression job. So we are able to remember more information and reproduce, like in a memory game, more of the signal if we find a regularity that can be compressed because of abstractions like repeat. So if you got a regular shape, like octagon, it's an old regular shape, it's easy for a human to just remember that as repeat 8 times some operation, whereas a baboon, that's his experiment, will not take advantage of that regularity, and it will be able to store in memory as many bits, as many points in the figure, whether there is a regularity or not, which means we are able to store things that have regularity better, and we can remember them better, because we create those abstractions that allow to compress the information in the world. And so this bottleneck that we have in working memory, like we select just a few bits, whereas the brain is huge, actually helps us to invent. Our brain does it. It's not something we do consciously. Invent abstractions that are good at capturing, in a compact way, what may be otherwise, a lot of bits of information in apparently.
So,
and it is consistent with the Bayesian interpretation, as I said, like, because the Bayesian procedure will want to this imagination machine to choose the solutions that require very few bits in order to explain a lot of things out there.
Want to jump in?
So just a little bit, I want to ask Joshua. So you mentioned that the symbols are learned in the working memory, and then those symbols get propagated to the long-term memory also in their symbolic form, or like?
Well, no, that's interesting, right? So what goes? I think there's a lot we still don't understand about memory, but what I think is consistent with what we know is what gets stored are parts of, if you think like keys, like parts of the pattern, such that when you set those neurons, the dynamical system will then go back to the attractor that corresponded to this symbolic compositional statement. In other words, your memory essentially is what it does is it allows you to recover these brain configurations corresponding to a particular thought from potentially a much smaller number, just like in Hopfield nets, if you remember these things. You don't need to set the whole network to the right thing. You just set some of the units, and it will kind of the dynamics will make it converge to a nearby attractor corresponding to a memory. It's exactly the same thing that's hypothesized in neuroscience. So the symbols are not stored like in a computer. They're stored by having some configurations of neurons being more likely, and then when they're evoked, that will entice the rest of the brain to associate all the other aspects that come with that memory and that correspond to the attractor of that memory.
So let me let's assume for a second that that we're going to have a neural substrate. So, and that those will be our building blocks. Then I think some of the works that we've seen are about ways to make those neurons act in a more symbolic way, let's just say, whether by being more modular or compositional, and therefore potentially being capable of generalizing out of distribution, as we saw in Tim's work, or also, reasoning, perhaps. So, what about or essentially representing causal relationships? So, what about what's standing in the way still? Of course, those ideas are in early phases, but of us making already a kind of large language model based on that kind of scheme. Tim,
Well-
any comments? This is accelerating you to 3 years from now.
Yeah, no, I mean, the work that I've been doing is less like a large language model, less sort of unsupervised in that way, and more like analogy. So it's more like trying to understand if you're given, as Joshua was saying, some kind of effective compression of the input, like in my case, it's a grammar for the input language that's abstract, then can you exploit that grammar to solve your task in some way? And the way that I approach this is by using those abstractions, so type symbols, and in my case, they're not dense vectors, they're just indices, to associate particular abstract concepts with particular procedures. So small symbolic procedures that can be composed to produce your prediction. So from my perspective, I'm struggling to understand a little bit this dichotomy between dense and symbolic representations at the abstract level, because I find that what I want to do, what my model wants to do, is to take I don't want to understand the contents of an abstraction. I don't want to represent the thing. I don't want to identify an abstraction with its some kind of summary of its contents. I really want a name. I want a name for the set, for that class, and I want to use work to be done in a local way with that single abstraction, in a way that we can sort of modularly compose that work. So there's a few different pieces going on, but one idea is abstraction, another idea is modularity, and a third idea is a kind of compositionality that blends the two to produce your answer. So I don't know. That's sort of, maybe that doesn't answer your question, but I'm trying to sort of thinking aloud about the.
But Tim, you want all these three things, but you also want learning, and in order to get good generalization, that's where the distributed representation becomes really useful. Right?
But this is exactly my point, is that I'm not using distributed representations, and I'm getting much better learning than I would if I were using distributed representations for this aspect. So for example,
Oh, well, part of it is your, I don't want to confound what you're saying necessarily with this, but part of it is you're introducing extra information, right? Which is the grammar and so on, and thereby dramatically reducing the number of samples needed, orders of magnitude, which is we can come back to also. Eleonora, I think in a way you're showing that as well in your work. You characterize it as improving performance, which is sort of, to me, the inverse of learning with less. For the same data, performance will get better. So by adding knowledge. So is that the kind of what you mean here, Tim, or something else?
Well, what I mean is that yes, so it's sort of irrelevant whether we're learning the grammar or we're given it. The question is, what is the representation? How are we using it? I mean, it's not irrelevant, but for the point you're making, and I'm suggesting that in some cases for abstractions, it makes more sense to not associate them, sort of identify them with their contents, their vector representation across some large number of features. It instead just makes sense to treat them as names of things and use them to, in a discrete way, to be able to pick particular modules that can deal with that abstraction in the task, whatever it is. So if I have 60 types in my grammar, for example, like a grammar for English, maybe what I want is a specific module for each of those 60 types. And I really don't need those types to be represented in a dense way. In fact, the relationship of those types to other types is represented externally in the form of the grammar, in the structure of the grammar. So I'm not convinced that dense representations are helpful at all levels of reasoning and learning. I think that at the level of an abstraction, a class of some entities, it may make sense, or at least it makes sense for us to talk about pointers, names, references, not contents, and to distinguish those two, because you really don't want, in deciding how you want to handle a class of data, you really don't want to necessarily overfit to the examples of that class that you've seen in training. You really want to kind of lift the analysis to something more abstract and predicate the way that you handle it on that abstraction and not on the contents. So I'm not totally convinced that there's no role for non-dense representation.
Tim, how do you handle, in a purely symbolic way, large-scale search? So, think of this like playing the game of Go. It's purely a symbolic problem. But what the continuous representations do is that they allow to discover incredibly efficient, computationally efficient way to search, like to find answers to questions in that symbolic space, which if you used classical search methods would just not scale. I mean, people have been trying to solve these problems of search in the classical search methods for decades.
Yeah, I think this is a good point.
And neural nets really nail it.
Well, I get that, but neural nets are what neural nets currently are, and they don't have lots of important biases built into them. So, for example, a feed-forward network has no implicit notion of abstraction. So, if you design your net in such a way with biases to accommodate those things that I was talking about, abstraction, compositionality, and modularity, then you don't need to have something that scales. That you have to train on.
You do,
1,000
because
GPUs.
if you want to scale your search, I don't see how you're going to do it otherwise.
Well, abstraction is a method for scaling search.
Let me propose that this is actually orthogonal. At least that's my view, because I do think, and we had some works we showed in previous instances of this meeting, using a reinforcement learning to do the kind of search you do in theorem proving. So ML as a way to kind of do better than search, I think is a real thing. But it's maybe just an extra kind of interaction between learning and reasoning, you could say, learning and symbolic things, but possibly separate from this representation question. So
inference could be used to answer questions, but it also is a crucial component in learning. So if you're good at searching, it's really you're good at inference. And in many cases, in order to solve the learning problem, think about if you have latent variables in particular, things you don't know but you have clues about. Inference, which is a search problem, is crucial in order for the learning to actually work. And so the machinery that replaces classical discrete search with neural-based kind of policy helps both. And if you're given the grammar, that's one thing. But if you want to learn it, then you both have a runtime efficiency of search, but a learning problem as well to deal with. And I don't see, except in toy problems, how you're going to do it otherwise.
Maybe the issue is really you've got these, you can clearly represent symbolic or discrete things as basins of a energy landscape in a continuous space. But maybe one thing we're getting at is indexing, finding the right one, kind of being able to point to it.
Naming these representations.
Naming. So what about that? And this relates to, maybe the practical issue of, you want to put in knowledge or you want to put in constraints somehow. And therefore, we use names because that's how we do it as humans and communicate with each other. So is that something you kind of lose by going, or when you go to the kind of continuous space?
Not necessarily. Again, go back to how your brain translates the activity into symbolic words that you're generating with your mouth or interpreting with your ears. So it's actually all continuous, but the pattern of activity corresponding to a thought, which is a discrete compositional object, translates in some part of your brain corresponding to controlling your mouth or interpreting signals from your ears into and from those high dimensional representations that correspond to a discrete compositional entity. So in other words, the continuous thing does the work, but what it represents are compositional discrete things, both in input, output, and in the middle with your thoughts.
So
Alex, just wanted to say that we have 20 minutes left and we have many interesting questions also in the Q&A.
Okay, let me just ask one more question. Just on a practical standpoint, though, from a practical standpoint, because as humans, we want to put in stuff and give them names. So like you showed Guy, and Eleonora, and having a semantic layer that represents in a neural net. Still, those are two representations. Although it becomes part of the neural net, it's specified in a sort of human readable language, right? So is that, and for that reason alone, we kind of need this. Is that how we should think of the symbolic part? It's how the, energy basins and so on talk to humans.
Think about LLMs. You've got symbols in, symbols out, so we can communicate with this thing. In the middle, you got a lot of continuous computation, which in some levels has discrete aspects like the attention. Not enough to my taste, right? But you can see that it's not very difficult to go from the continuous to the discrete and vice versa at the input and output level. So now what is missing in the LLMs is to be able to use language to refer to the internal symbols. So that the thoughts are missing there. It's just like you go directly from hearing to speaking, and the current systems don't have an intermediate symbolic latent representation for your thoughts. So it's like right now we don't have thinking machines. We have machines that are just blurting out the answers without thinking.
Any comments from anyone before I go into the
Well, I think it's pretty clear. Sorry. I'll let you speak after me.
No,
I
go
think
ahead.
it's clear that we need both representations. What I found Les Valiant's robust logic stuff to be very interesting is that he, uses continuous space to do the learning. But once that's done, he switches then to discrete logical reasoning part that absorbs the uncertainty that comes with advantages as well as disadvantages of the continuous space. And I think we need a ladder to communicate properly with the users and make sure that the system is trustworthy. So sorry, Eleanor.
No, no worries. I mean, my point was kind of similar to yours. I just would like to add a further thing, which is like we are building AI for humans in the end, in my opinion. So like we are not building it for, at least for me, I'm not building it for the sake of building an AI. So the user in the end is a human. So forgetting about it, would be, I don't know, crazy in my opinion. So we need a layer in which we can communicate, right? So having some symbolic representation at a certain point is important. Then, for example, I don't know what you think about like those models that create intermediate representation. So there were some language models that, for example, were sampling words to explain their own reasoning, right? So that was back to the point of rooting of, instead of trying to explain models, like create models that are interpretable by themselves. So it's not exactly a symbolic way of doing things, but it's like having transparent layers and black box layers, sort of one after the other. So that could be, for example, a way of going, which is very much close to what Naoki was saying.
Guy, any thoughts, comments?
Yeah, I can maybe give my perspective. So I look at neurosymbolic AI from a kind of more algorithms and data structures perspective. And don't get me wrong, like I think neuroscience and cognitive science are super interesting and very worthwhile to study. But for me, I don't really draw much inspiration from them. I think a lot of the discussion about discrete continuous, what is a symbol, I think is actually it's not so clear cut for me. For example, for me, it's all about reasoning. So can we compute marginals? Can we condition on constraints? Can we give guarantees? And so I can do that on pixels. I can say, I want to, guarantee that, this left patch of my image has certain pixel values in it, and my pixels are symbols. Or I can guarantee that the function I learn is monotonic, meaning that, I can have some logical constraints between inputs and outputs. Is that then suddenly making my number that I'm predicting is a symbol? Sure. I can say this neural network for some vision problem has to be translation invariant. Is then my axes, my 3 dimensions of space are data and symbols? I think it's a little bit arbitrary, and for me it's really more about can we give to these architectures the ability to do certain types of deductive reasoning at inference time. That doesn't just mean let's train a model on some examples of what should be done, but actually do some form of what one could call deductive reasoning. And so that's a very different perspective, I think, to neurosymbolic AI, where it's really not about distributed representations and what happens in the brain and so on. It's really about algorithms for me.
Comments from anyone?
Yeah,
I think you
I
could
agree.
start from. Oh, go ahead. Go ahead.
Oh, I was just going to say, I mean, there's a question here about if you have a symbolic representation, then certain algorithms, symbolic algorithms, are more effective with that representation. If you only have a continuous representation, then you have to use other algorithms. And so I think it's not totally clear to me that one style suits all purposes in the brain. I think there are things like reasoning that just work better when you have symbolic representations that may be derived from, certainly are derived from underlying neural representations, but I don't think that you would necessarily want to solve your problems that way. I think there's there's an efficiency value in moving to a symbolic realm, and it's hard to believe based on human behavior and cognitive science experiments that people don't make use of those kinds of symbolic algorithms at some level in the way that they compute.
Yeah, maybe to back up what Tim says, I think on the question of can you just do pure search to solve Go, well, obviously, neurosymbolic hybrid approaches have done really well, but I think people also now find that whatever the learned policies are, they are very, very easy to attack adversarially and, move the game to some area of sample space where the policy really does ridiculous things because it doesn't really reason about what to do there. It just has this knee-jerk reaction of like, what have I learned in embedding space? And so those are the weaknesses of the search in purely embedding space, right? And I think we need some combination of both. Yeah.
Could I offer a quick thought as well? Because
Yeah, please.
we've talked about communication a few times, and I thought I would just point out that we do exchange words and phrases with each other. They do seem to be discrete objects, but that's only the beginning of communication, is recognizing those things. Actual communication is recognizing something like an intentional state, which is difficult to articulate, certainly very high dimensional. And so these symbols, they're modulating all the time based on the context, ambiguity, vagueness, pervasive throughout language. And so I would think instead about what happens in communication with these words and phrases just as vehicles that help us figure out how to coordinate. And the coordination part is what matters. When we talk about symbols, that's simplification, because these individual symbols play so many roles when we actually interact with each other.
Can I add one simple thing here? I agree that, for example, in a language, there are a lot of shadows, let's put it in this way. But machine learning is going to be pervasive, right? It's going to have an impact on every aspect of our lives, right? And if you think about technology that is pervasive, when we go back to sort of what I do in my research, you need to have requirements. Now in requirements, you don't have space for shadows. At that point, you need to have some sort of certainty. When you build an airplane, you don't say, oh, maybe it should be at this altitude. You have a fixed value for that. So I think where neurosymbolic can play a very good role, an interesting role, is that it can model the shadows, but when it's needed, when you, for example, want to comply with requirements, it can be crisp. You can model hard constraints. And I think symbols play a role when, for example, you want to certify things. Like I would expect at a certain point Europe will want us to certify AI. So we won't be able to certify every single neuron, but we can say we won't make these mistakes because we will have a bunch of requirements telling us these mistakes won't be done. So I think symbols can really play a role when we want to go like into crisp, into hard constraints, for example.
Francesca, do you want to comment on that?
No, I agree with that. I mean, I have the same, feeling that really communication with human beings, but also the ability to have some certainty about behaviors. That I think that the symbolic part can be useful. I also think that, I mean, I believe that neuroscientists and cognitive science have studied our brain, our mind, and maybe they tell us that the symbolic part is not there. I mean, it's just something created and not ever being present in our mind in any way, rather than supported by the non-symbolic part. But that doesn't mean that our machines need to mimic exactly what, I mean, machines have very different properties, and they can do things that the brain cannot do already now. So I'm saying that not necessarily to build a machine. Yes, I think we should get inspiration for what we know about the only form of intelligence that we know, which is the human being. But not necessarily that everything has to be like that, for many reasons, for certification, for hard constraints, for communication with human beings, for all these reasons that we mentioned. Not necessarily we have to mimic exactly the fact, whether human brain has only a non-symbolic representation, and then symbols are built and are supported by that, but there is no space for really a symbolic place. So I don't think that machines necessarily have to do that, because we have to be clear about what's the goal of building these AI machines, as Leonora said. No, is it to build something like a human being, or is it to build something that is useful to human beings and with human beings, and can work, can improve our creativity, in innovation, and so on. So that's why I also posed earlier on, the question about value alignment, which I also think is what Eleonora and what Guy talks also was related to.
So
I also want to say that, and not Joshua knows that I always have in the back of my mind, when I'm inspired by my knowledge of how the human mind works, I always have this question of, is that a bug or a feature in the human being? Because we have some limitations. Maybe something that we see that is done in the human being, it may be a feature to be transferred to machines because it's very useful. But something else, maybe a bug because of a consequence of our limitations. And so then I'm not sure how to recognize the two, but I think that question should always be there in transferring information from the knowledge from the human being to a machine.
So I'll give
Sure,
it to Joshua to respond, but we can do it. It's related. There's a related question
Yeah.
for Joshua from the audience. Does this necessarily mean that the reconciliation of neural and symbolic must be in principle bidirectional? Go ahead, Joshua.
Well, we can do what we want, but in the brain it is obviously bidirectional, and with the sort of dual representation I've been talking about, where things like statements, short sentences that are symbolic and compositional get associated with high dimensional vectors. You get both right, at the heart of the matter. And of course, we have symbols coming in, symbols coming out, and continuous computation. In the middle, some of it has a symbolic interpretation, and I kind of suggested one way that it might be going on in the brain. But I want to go back to the question of alignment. So I agree completely that the way human brains implement intelligence probably has advantages and disadvantages in the whole spectrum of potential intelligences. But we don't understand enough. And clearly we don't understand enough of the principles of how brains are able to do the incredible things they're doing, to just discard because we don't understand something. And we're not sure how to implement like symbols that are brain-like. But regarding alignment, I want to mention something that's maybe more mathematical in that question, which has been like well explained in Stuart Russell's 2019 book, Human Compatible. So the issue with alignment is that it's very difficult for humans to precisely express our values, our expectations. This is a well-known problem. It's called the alignment problem. It's a problem that's been studied in economics. In economics, it shows up if entity A wants to subcontract a job to entity B. So A is us, B is computer. And so entity A is going to write a contract that says, in such and such circumstances, you should do this, and then you're going to get your reward. But entity B it might not do exactly what A wanted, and the reason for that is that in a reasonably small contract, you can't enumerate all the possible behaviors that B should take. In the same way that it's impossible for us to specify how a very rich computation going on in a large neural net should be. And in fact, it's not just neural nets; it's a more fundamental problem. So, what's the solution to this? Well, one possible solution, because otherwise we're going to have problems, machines not doing what we intend, is for the machines to maintain a Bayesian posterior distribution over what they think we want. And if you do that, what's happening is when the machine maintains that uncertainty, it knows that some action could be good or could be bad because there's uncertainty. And it knows that humans will act according to their preferences. And so the actions that it would take is, well, don't do anything because I'm not sure if it's going to hurt or it's going to be good. Whereas the human presumably knows better because it's going on in their brain. And so it's a cartoon that I'm explaining here. But what I'm saying is, if we unlock the problem of approximate Bayesian posteriors, which I think neural nets can do and will do, and do in our brain, then we can help with this issue of making sure machines don't harm us, do the things we intend, or at least don't harm, like medical doctors, by acting in a way that is not good for us because they misinterpreted what we actually wanted.
Joshua, can I follow up on this? Maybe this is what you're saying. My reaction to what you were describing is that, of course, people are very complicated for lots of reasons. So contracts between people will be endlessly hard to
Yes.
resolve and have all sorts of vagueness about them. But can't we expect more from contracts between us and machines? After
No.
all, we have a lot of control over them and a lot of ability to
No,
study
it's a
them.
mistake to think that. And the reason,
What's the mistake?
yes, it is a mistake. I mean, in some special cases, we can write a precise and complete contract. But for most tasks, like, where we want to deploy AI these days, like natural language, dialogue, and any other thing, like your robot, for all of these tasks, the state space is so complicated and high dimensional. It is impossible in a, age of the universe or size of the universe scale to write down the contract that would do exactly what we want.
Oh, I'm surprised that you're as pessimistic as you sound there.
I'm not pessimistic.
The
This is
problem with
mathematics.
people is that we have such limited access to them, and they have their own desires and goals and
No, but
everything.
we are
no
not even
insight into.
able to express what we want in a compact way between ourselves,
No,
and
but,
much less to a computer that doesn't have the same priors.
But I think that Chris is what is mentioning or what is referring to, in my view, is that we are not building or designing another human being. While we do build and design a machine.
Yes.
So we have more power in how the machine is going to behave
Yes.
rather than.
And we still don't know how to state what we expect from the machine, because that is an object that's exponentially big.
But wait a minute, we do between ourselves, between humans, we do.
Yeah, and it's
express
imperfect.
contracts, right? They're imperfect, but it's pretty compact. I mean, it's like the laws of the United
Yes.
States.
Yeah.
Yes.
And we can whatever.
And you
the
got
standard is for
companies,
humans, we can
taking
do better
advantage of
with a machine.
loopholes.
Yeah.
You got companies taking advantage of loopholes in contracts because the contract is incomplete. By the way,
Yeah,
the
I think
2016.
we might be saying the same thing then, right? Because you're saying between people, this is hard, but we pull it off. It's going to be
No, we don't pull
marginally
it off.
easier.
We live with the consequences of not doing it right.
Well, we have contracts that work between people, despite all this.
No, the contracts are being violated all the time. So, what do you think
Well,
is
I'm not
happening?
saying that, but we have functional contracts between people. I grant you that there are cases
Okay,
where
in
they don't.
simple cases, of course, we can do it. But so think about what companies are doing. There's a contract between companies and society, which is respect the laws. You're allowed to maximize profit, but respect the laws, and hopefully that will be good for society. But fossil fuel companies have been blatantly cheating, and not telling the truth about climate change, for example, and
But that's not because it
tobacco
is.
companies.
But not,
It's an alignment problem. It's because we haven't been able
but not
to
because
control them properly.
We
yeah,
might
but
be saying the
Joshua, they
same
were
thing.
doing
Joshua.
that not because they didn't understand the contract, because the specification was, but because they saw that they could be more convenient for them acting in a different way. So they were aware of the constraints. So it's not that a
But
problem of
they have lawyers whose main job
yeah,
is to make sure that they act legally,
incomplete.
but in a way that maximizes profit, not necessarily that satisfies the intent of the law,
Yeah.
just the letter of the law.
But how to
Nora,
emphasize again?
you had opened with in your talk about AI safety that you can't necessarily solve it, but you can alleviate it. Do you want to comment on that?
Right.
Yes, so that's actually what I want to say. So I think in software engineering, requirements elicitation, like the completeness of the requirements that you want to state is it's a known problem. You will never state the complete set of the requirements of your problem. However, I think companies still do it, right? In the law, we still try to write laws. So the fact
Often
that
less.
we are not able to write a complete set of requirements shouldn't make us afraid of writing some. So at least we should put some guardrails, which are already there for LLMs, right?
Sure.
To avoid the worst case scenarios, right? And we cannot just give up just because it's the set is exponential. We write some.
Yes.
And that's why I say in my talk, how can we alleviate the problem?
And we use another trick in society, which is we have judges. So what judges do is they interpret the law. So even though the contract isn't very precise, from the point of view of a computer, you say it's not precise enough. The companies know that some humans are going to be checking after the fact. So, but it's that's a big part of our protection. But if a machine harms us, yeah, maybe it's too late. Like we need to find ways to avoid this as much as possible before it happens.
From the audience here, incomplete specifications are unavoidable in any system. Paraphrasing, but this can evolve. You can learn from failures and formulate more safety constraints.
Yes, you can always improve.
Yeah, and just for the record, I was not saying people are easy. I was saying that people machine is a little bit easier. But none of these things are easy simpliciter. Yeah, I just want to be clear that that was the organization of these things. And we pull it off for people. There are problems, but we pull it off for people. And I'd be even more optimistic about pulling it off for systems that we have complete control over and can experiment with in many more ways than we can experiment with humans. For example.
Just to come to another point, which is reasoning, which is kind of related to, I think, even this point about alignment, because to success, we can write down as we do laws, but then they get interpreted through a process of reasoning and to see how they apply to a current situation and so on. So arguably reasoning is required to fully implement, rules and concepts that we, which represent what we want. So, and therefore the ability of our machines to reason, reliably is important. And Guy, you were talking about reasoning in a few ways. One is about successful. People leaving. Who did we lose? Okay. Oh, we lost Francesca. Okay. So do you want to and that another thing which Yashra brought up was actually faithful probabilist or representing probabilities sort of properly, as opposed to just the frequency of word mentions. Do you want to comment anything about that?
I mean, I can mention that I definitely agree with Joshua that things like marginalization and reasoning about the distributions we learn is really important. I think my approach to this problem is a bit different. I try to come up with deep generative models that can do this out of the box exactly and efficiently. So there's not really the reasoning problem is kind of solved as part of the architecture.
Out of the box without training?
No, like you train a model, let's say a transformer, but somehow you can also ask it for marginal probabilities, and they will be exactly those marginal probabilities that you want, that you've actually learned as part of the joint, the likelihood function.
Exactly.
Yeah, exactly. So these things are called probabilistic circuits. And so my approach
but then
is
you're limiting the set of distributions that you can represent, right?
No, you just you might that you can compactly represent. So the question is, can you still get good likelihoods? And then that's the game, right? So then you have to improve I mean, every architecture is limited in which distributions it can represent compactly, of course, right? You always have some way of encoding an exponential table into some smaller set of parameters. So this is not different from any other neural network. And so I do think that being able to ask, let's say, the marginals that Joshua wants to see, that this is helpful for alignment and safety and so on. I mean, it's probably not sufficient, but yeah, I do believe these things can help explain the model and what it has learned.
So when we have, when we're looking at making sure that our machine can reason reliably. So whether it's deductive reasoning, where we have definite inference rules and they can only be applied at certain times and so on, and we can prove then that the such and such process is sound and complete. Or in probabilistic inference, we have certain things operations you can do at certain times. You can marginalize, you can do this, you can do that. You can, if you have conditional independence, then you can do this, but not that. So these are rules of inference that when we use a symbolic procedure, we can be sure that they're being applied properly and the resulting inference is correct in various senses, depending on the kind of reasoning. So when we learn to reason, we're not necessarily enforcing that constraint so far, at least in some approaches. So what do we, now of course, as Joshua brought up, learning can accelerate these kinds of searches, but still there's this other element that of making sure that whatever it is that we're going to do, it actually follows only correct steps. So any comments on that? How do we achieve that and yet get some of the benefits Joshua was talking about with continuous spaces accelerating search?
So I've already said this, but I think that Les Valiant's proposal was exactly on that point, to absorb the uncertainty, probabilistic uncertainty, and so forth that's involved in learning, but still try to come up with a system such that you have pack guarantees on both sides. But of course, I think there's a lot we can improve on it with the modern technology from deep learning and so forth. But I think the idea was there, no?
Just a reminder of the time.
Yeah. Maybe we'll chop it soon. But any last comments on that? So Joshua, you wanted accurate probabilities. So what would you say?
So I don't think that we'll get crisp, exact probabilities and reasoning from neural nets. Neither do human brains give us that. But what you can get, so in my talk, I talk about some objective functions that have the property that if you minimize them, you'll get the correct probabilities out of the box, sampling or marginalizing. Of course, in practice, when you train a neural net, you never get the loss to be going to a global minimum. But the nice thing with this way of thinking is the larger the neural net and the more you train it, the more it approaches the correct probabilistic inference that you're after. And so I think that's encouraging. Think that the current large neural nets that we have, they're still tiny compared to your brain.
Good. So
I have one response. It's more of a question, but so implicit in your statement is the sense that neural nets as they exist now scale well. In this, not computationally, but they scale
too.
Well. So there's many examples where large language models have anti-scaling properties. They in fact do worse on important problems. So what is
because
the
I don't think we're
response to
training
that?
them the right way, but that's a different question.
Well, that's my point. How do we know, how do we build in the things that are important, like reasoning, so that they do well on those and do.
I agree. So this is the sort of thing I've been talking about. How do we design their training framework so that they're really geared to doing reasoning, and that in the limit they converge to the correct reasoning on the large scale.
This is fantastic.
I'm not saying this is a solved problem, but I think it's feasible.
So we got a point of agreement. So on that note, well, let's do closing thoughts. So let me just go around. Tim, I'll consider that your closing thought. Asim, closing quick thought.
Yeah, so not related to this particular discussion, but overall, I wanted to thank you, everyone, and it's been amazing. So I got loads of comments, not only through this channel, but through email, through social media, everywhere. So I want to thank all the speakers, all the attendees for joining the seminar.
Oh, no, that was too nice to see him. I want little controversial statements. All right. Okay, Michael.
Yeah, so in general, I think there was a lot of debate how to represent symbols. And I think representing them with distributed representations is still quite beneficial, and you can all gain those benefits of improved search, etc., accelerated search, while still like being interpretable and transparent. So I think this might be for sure like one way to go forward.
Guy.
Yeah, I would like to maybe kind of reiterate the beginning of my talk on the paradox of learning to reason, saying that if you want to learn the reasoning function just from data, you'll probably learn something that almost minimizes your loss, but it won't be doing reasoning. It will be doing something else. And if you give it a different set of reasoning problems, it will probably fail miserably. So that's something to keep in mind as a risk when you try to do everything through data and loss functions.
Eleonora.
I think, like, as a concluding remark, I would say I don't see this big divide between crisp and soft. Like, I think the neural networks give us the great ability of going from continuous to discrete and back to continuous. And I think we should play, because I think like circuits, as we know them as of now, they're completely crisp. Humans are mostly soft, I would say. And I think with AI now, we have the ability of going on both worlds, and we shouldn't give up on this ability.
All right, Naoki.
Yeah, no, this has been very educational, and I'm very excited to learn about all these different approaches. But they're all, sort of approaches to bring together the two aspects, including the importance of discretization phenomena and minimum description length that Hersche was saying. Really excited to find out more about those things. I used to be believing in MDL too. So thank you, everyone.
Chris.
Since efficiency came up, I'll just mention data in that context. So I think that even all the symbol streams and all the images and all the videos on the web, that's still a very strange slice of the world that we live in. I think there's no in principle obstacle to a language model, for example, trained on all those symbols, learning what chocolate tastes like in some deep sense, but it might be a very inefficient way to learn that fact compared to the chemical, physical thing that happens when some creature like us tastes chocolate. The more we could push toward data that have that full experience that we regard as the human experience, the more these models are likely to, in a data-driven way, learn very rich conceptual structures, and then there'll be more to explain, and I think they'll be more powerful. Trust is a separate thing, but they'll certainly have more interpretable conceptual structures, and that will be reflected in their behavior.
Joshua, I'll give you the
Probably
last
not a big
word.
breakthrough on data.
Oh, sorry. Joshua,
It'll require a breakthrough on data. That's all I wanted to say. Sorry.
Oh, okay.
Yes, I'm a machine learning person, and the central question in machine learning is sample efficiency, like the ability to generalize from, as little data as possible and generalize as well as possible. And the way I think about symbols and reasoning is as an inductive bias. In other words, some constraints, if you want, or some ways of doing things that restrict the set of solutions you would otherwise be looking for in machine learning that provide much better generalization. And in particular, as I talked about, the causal reasoning out of distribution generalization, which is something where we need a lot more progress in machine learning.
Awesome. Well, let me thank everyone, and you all delivered. This was fantastic. So thank you for the good wrestling and excellent intellectual discussion. So
thanks for organizing.
Yes, thank you.
Thank you very much.
Yeah.
Thanks, guys.
everyone,
Thanks.
take care.
Thank you. Bye.
Bye.
Bye. So